Welcome to lesson 2, example number 1. And before this, they go through the types of beams and the types of loads. One being a simple beam, one being a cantilever beam, then a continuous beam, an overhang beam, a fixed end beam, which has two fixed ends, and then they go to concentrated load, uniform load. And these are your major things you're going to need to know for beams, and I would go over this and know those things, and they do a pretty good job of explaining what they are. A simple beam being two supports with no moment resistance on either support. Typically one's a one's a pin and one's a roller, giving you 3 different reactions. But since there's no horizontal loads, then your vertical or horizontal reaction is 0. And then the cantilever has 3 reactions. You have a moment, a vertical, and a horizontal at the wall. So, and then you go on to your overhang beam, which one of them will usually be a pin, and then the other one will be a roller. So you have 3 reactions, and typically you want to have 3 reactions per member. And I don't think they've gone over this as well, but we'll go ahead and go over real quick what determinate is and indeterminate. Determinate. My pen is acting up right here, and it's hard. And indeterminate. My pen's acting up, so it's hard to write. What determinate is means it's easy. Well, for right now, I'm not going to go into depth on this. Determinate, it means it's easy to figure out. You can determine the loads very quickly using a free body diagram. Indeterminate means you're going to have to run more of like a more difficult analysis to figure it out. It depends on what your section is. Determinate, to find your loads, your moment, your shear, and your P load, your V load, P load, and in other words, your V, your P, and your moments. You don't need to go into a difficult analysis. You can do it real quick by shear moment diagrams, or you can do it very quick by cutting your beams, and you can find it out pretty darn quick. And to figure this out, what you do, and hopefully I can get this in real quick, but you have the number of members you have needs to be equal to 3 times the number of reactions. For instance, we have 1 member right here, and we have 3 reactions. And some people write it like, you're right, it's R equals 3N, and N equals your number of members, and then R equals number of reactions. Some people will abbreviate reaction, RXN. Just gets a little bit simpler way to do it. So it's determinate if you have a free body diagram and you look at it. Okay, well, we have 1 member, so that's 1 times 3 is 3, and number of reaction is 1, 2, 3. So that's a determinate. And then you can also have more complicated ones. For instance, you have, let's say this is a fixed, and then let's say that for some reason this comes in like right here, and this is a roller. This is a pin, this is a fixed, and this is a roller. So you have 1, 2 members, and then you have 1, 2, 3 reactions here, 3, 2 in a pin, and 1 on a roller. So that's 6 total reactions, 2 members, 6 equals 3 times 2, and we're good to go. And I'm going to just do a video on determinant C, because I'm not giving it justice right now, but I'm going to go ahead and move on, because they didn't go over it. Maybe they're going to go over it later. But we're going to skip over it right now, and we're going to go ahead and move on to solving example number 1. And example number 1, I haven't got to look at it, but it is determine the reactions R1 and R2 for the beam shown, neglecting the weight of the beam. And this is pretty straightforward, actually. We kind of did some of the same stuff last chapter. Hopefully I can get this in, but this is R1. And if I have time, I'll go ahead and do a shear moment diagram on this as well, and that's a big if, because I always run over on time here. This is 8 foot. This is 6 foot. And then we have a distributed load, and they talk about distributed load. It's kips per foot, or pounds per foot, or pounds per inch, whatever, but we have 300 pounds per foot. And I'll write PLF means pounds per linear foot, and then 1,000 pounds. And that's at 6 foot. That's just right up here, 6 foot. Alright, now if you remember, we have the 3 equations of equilibrium. The sum of the moments about a point equals 0. The sum of the forces in the x direction equals 0. And then the sum of the forces in the y direction equals 0. This is a free body diagram already. Sometimes they'll show a pin connection, you have to say, oh, that's a pin, or they'll show a roller and you have to say, oh, that's a roller. But once you have this is the basic free body diagram. Now what we want to go to is we want to take a look at it. We want to figure out the reactions. And that's the first step in getting to a shear moment diagram, but right now they just ask for the reactions, so that's all we want to do. But we'll try to go a step further. We'll go fast here. But since we don't have any forces in the x direction, so that's not going to help us. We have 2 forces in the y direction, so we can't really separate one of them. We can't do that. So let's go ahead and do the moment. And if we take the moment about, let's call this point B, and this is point A, then we can separate R1, and we can solve for it, because R2 will equal, the moment of R2 will equal 0. So the moment about, I'm going to go ahead and do B. You could do either. It would work. The moment, sum of the moments about point B equals 0. And we're going to say this is the positive. And we'll just go left to right here. R1 is going to create a positive moment, so we'll just keep it positive. R1 times, what is that, 8 foot? And then we want to keep going. We're going to subtract 1,000 pounds, because it's going to be a negative moment. It's going to go this way, which we said was negative, since the other way is positive. That's at 6 foot. And then we're gonna, and then we haven't done this before, but you're gonna look at it and you're like, oh shoot, well, I don't know how to do that distributed load. What do I do? And I'm gonna bring it down here just to show you how it's done. You have a distributed load, and it comes from calculus. The area under the curve, if you will, is what it equals. But all it is you have 300 PLF, 300 pounds per linear foot, times 14 foot. .300 times 14 foot is 4,200 pounds. So overall, you're going to have 4,200 pounds. Come on. There we go. And this, actually, it's going to go at the centroid, or the center of gravity of that load. So for this, just the basic uniform, they call it uniform because it's the same right here, at the left side as it is the right side. It's a uniform distributed load. So it's right in the middle, because that's where the center of that load is, the centroid of the load. Now if you have a non-uniform distributed load, let's say, this is 300 over here, PLF, this is 0, PLF right there, and you go down along there, then where's the centroid of this load? Well, if you look in the centroid of a triangle is 2/3 over. So you could, and this is 2/3 of x, but you would say 2/3 times 14 if we're talking about this example, is where that load will act. But we're not dealing with that. We're dealing with a square or a rectangle, and that is at 7 foot. So we're going to go ahead. I always like to put a squiggly line for a load, just to say that is it's a uniform distributed load. It's the equivalent of the uniform distributed load, and you'll see, well, it is the same. It creates the same moment as that uniform load. 4,200 pounds at 7 foot. 7 foot from B creates the same as 300 pounds per linear foot times 14 feet. So we go over here, and that's going to create a negative moment. So we're going to say negative 4,200 pounds times, we said 7 foot. Now we go ahead and solve for R1. And I'm not going to go through the steps here. I'm just going to do it all in my head, so I hope you can follow it. And I'll kind of show you what I'm doing. Okay, R1's positive, so you want to leave it there. You have negative 1,000 plus negative 4,000, so that's going to be negative 5,200. Oh shoot, I'm going to multiply it first, sorry. Cancel what I just said. 1,000 times 6 foot, that's negative 6,000 plus 4,200 times 7 is negative 35,400, and then you're going to flip it over to the other side so it becomes positive, so it's a positive 35,400 equals R1 8, so you want to divide it by 8 to get rid of it. So you have R1 equals 4,425 pounds. I'm going to go ahead and check that, and where is it? There it is. R1 equals 4,425 pounds, so we're good. Now we only have one force in the y direction reaction to solve for, so we can go ahead and do the sum of the forces in the y direction equals 0. You can still use this. It comes back to when you're using free body diagrams and you're going into shear and moment diagrams, you'll notice that you have to switch back to the uniform distributed load. But not right now. Right now you can just say, okay, I'm solving for reactions. I can continue to use the equivalent load. So you have negative 4,200. You have positive 4,425. And then you have another negative 1,000 pounds. And then you have a positive R2. And I'm going to go ahead and solve this in my head again. Well, you have positive R2, so I like to keep it on this side. But you have 5,200 plus a negative 100, so it's negative 6,200 plus 4,425, and you divide it out, it's negative, and you're going to get 1,775 for R2. And let's check that. Actually, I messed up the math here. I messed up my math, and I got 775, and that checks out. I did 4,000, that gives you 5,200 minus 4,425 gives you 775 pounds, and that is R2, and that checks, and R1's 4,425, and that checks. I'm going to go ahead and do another video on